Any businessman who needs to move quickly in a 300-mile radius can now enjoy the productivity and freedom previously reserved for conglomerate presidents and board chairmen. Private transportation has gone about as far as it can go on the ground. Space-consuming urban airports are no longer in vogue. The logical way out is not to crowd existing terminals further, but to utilize the almost vacant airspace well under high-density air lanes. Windstar is the perfect answer. Through the dedication of a team of rotorcraft professionals, the promise of three-dimensional flight has found its fulfillment in historical fashion. To learn more about Windstar, its developers, its features, and its ability to propel your business into the 21st century, we take you to Vertical Lift Technology's Windstar Center.
Hello, I'm Ron Anderson. Welcome to Windstar Center. We're here to introduce the next generation in helicopter design, the world's premier four-place piston engine helicopter, Windstar. In 1939, Igor Sikorsky's VS-300 helicopter made its appearance. Now, almost 50 years later, there are still only 20,000 civilian helicopters operating in the U.S. By comparison, in 1908, Henry Ford started building automobiles. Only 20 years later, 15 million had been delivered. With the exception of pilot training, the reasons for the lack of helicopter production are the same as those for the early automobile. First, high cost. Second, too complex of a machine requiring extensive maintenance. Windstar is no ordinary helicopter. It addresses these two reasons in a way that no previous design ever has. In conceiving Windstar, attention was paid to an observation by Albert Einstein. He said, "The invention of compound interest has had more effect on the world than harnessing the atom. Therefore, the best way to reach the full potential of the helicopter is to compound the improvements, especially improvements to those elements that currently limit helicopter use, namely safety, noise, and cost." Interestingly, these are the identical improvements that were required during the evolution of the automobile. Think about it for a moment. A four-place helicopter is no heavier than a four-passenger automobile. And if anything, its parts count is less. In 1982, at the American Helicopter Society's annual forum, Bart Kelly correctly predicted that somewhere within the next 10 years, there would be a very great effort using the most sophisticated engineering to develop a cheaper, more reliable, mass-produced helicopter, and it would be piston-powered. Safety, comfort, quiet operation, ease of maintenance, a piston engine with a backup power source, all at an affordable price. These were the chief motivating factors in the development of Windstar. Now, it's well known that product and market follow the chicken and egg cycle of vision and sweat. And to be sure, development of Windstar has taken a large measure of both. You may wonder how Windstar could emerge from a small company in the desert outside of Phoenix. The answer lies in the person of B.J. Schramm, president of Vertical Lift Technologies. He has a triple threat capability as a helicopter designer, test pilot, and manufacturer. His insight to utilize the compact five-blade rotor as the basis of his design, his visionary projection of the demand for helicopters, and his wisdom to exploit the technology available in composite materials, electronics, and engine design has paved the way for the revolutionary Windstar. If this compounding of ideas for Windstar sounds simple, it was not. It's taken several years of component development, such as the all-flexure composite rotor and high-power density engine, which is based on Schramm's extensive foundry experience. It required the assembly of key talent, men like Al Balauer, former chief engineer for commercial helicopters at Boeing Vertol, Mr. Hans Hermann, engine consultant with Porsche, BMW, Offenhauser, and Chrysler, and Mr. Oswald Webb, chief engineer of experimental design for GKN in England. It has also required the assembly of a group of foresighted investors blessed with the ability to see beyond the risk and to focus on B.J. Schramm's vision and dedication. The Windstar development program encompasses the latest technology and design techniques pertaining to the airframe, rotor system, power transmission, and engine development programs. These various systems were developed concurrently. One of the key aspects in the Windstar development program is the fact that the manufacturer must have the ability to not only construct the airframe, but to build the power plant from scratch.
Here we have the crankcase. The case halves are held together with the cylinder heads by means of through-bolt studs. The crankshaft has a generous bearing area with 4 main bearings. The front main bearing has a thrust surface on either side to absorb thrust either way on the crankshaft. The rockers are actuated directly by the cam. The cam lobes are unique in that they are pointed on one side of the lobe. Both camshafts turn in the same direction. This head is a combination water jacket and cylinder head in one casting. It is similar to the Offenhauser racing engines and is probably the lightest way to build a cylinder head water jacket unit. The total weight of the cylinder head with the liners is under 35 pounds. The layman frequently misunderstands what it takes to build a power plant. If one can build a cylinder head, the crankshaft, and the rods, one can usually build an engine. The cylinder head is normally the most complicated part, especially from a foundry tooling standpoint. These are the permanent tooled shell core boxes for producing the 9 different shell cores that are used in making the cylinder head. The cylinder head casting has 10 cores interlocked together. This is a complex piece to produce from a casting standpoint. However, it greatly simplifies the time and accuracy in machining. The cylinder head is double poured. The rate of pour is important so that the proper metal flow is attained as it enters the casting. The cylinder heads will be made on automatic molding equipment that will allow us to make a mold every 5 minutes. The engine is both turbocharged and fuel injected. The fuel injection pump is driven off the end of the crankshaft. It supplies pressurized fuel to the butterflies through 2 lightweight log manifolds. They feature slip joints for engine expansion and contraction. From the intake system, we go to the exhaust system. The turbocharger is driven by exhaust gas passing through 2 log manifolds. This unique exhaust system features stainless steel castings with slip joints employed between each port. This prevents the irritating and common problem of exhaust system cracks. Hot exhaust gases may bypass the turbocharger through a unique bypass system. A piston opens the precise amount in proportion to the manifold pressure sensed.
The ability to design an engine from a clean sheet of paper allowed the further benefit of a multi-port fuel injection and twin ignition. We have an ideal opportunity to burn a relatively lean mixture. High swirl, lean burn technology is not new in automotive circles. However, it has not been employed in aviation power plants until now. A high swirl is achieved by careful design of the intake tract and combustion chamber. Racing engine designers have developed high swirl technology to the point that horsepower increases of 25% with the same fuel economy have been achieved. It's the utilization of this kind of technology that gives Windstar its turbine-like performance.
To ensure the necessary perfection in the key components, numerous complex pieces of test equipment were designed in order to prove their reliability in the initial prototype. Without the perfection of each of these mechanisms before initial flight testing, the developmental flight test program would have turned into chaos. After installing the power plant into the engine transmission fixture, the full torque load of the engine is applied to the helicopter drivetrain to determine that the transmission will operate properly. We look for signs of overheating, and after extensive running, a complete transmission teardown is conducted to inspect each part for wear. This testing will also determine the integrity and performance of the centrifugal clutch and the elastomeric torque absorber that connects the power plant to the transmission.
The testing phase in the engine transmission dyno proved to be most effective. Not only was the engine mated to the transmission, but the centrifugal clutch mechanism and torque absorbing system were tested concurrently. One of the most exciting features of Windstar is its new hingeless, bearingless rotor system. The major contributor in its development was Mr. Al Belauer, former chief engineer at Boeing Vertol. Mr. Belauer made his contribution in the aeroelastic stability analyzation of Windstar's rotor. In addition, his stress analysis work on the main shaft and transmission attachments helped keep strength high, weight low, and design simple. Windstar has the first patented rotor system under 3,000 pounds that does away with bearings and even eliminates the rotor hub itself. The hub becomes merely a stamped, contoured plate to which the blades are bolted. With its composite construction, the blade can be shaped with the most efficient aerodynamic configuration from tip to attachment.
Fatigue testing of Windstar's rotor is accomplished by applying the flight loads which the rotor system encounters with the test equipment you see here. This machine applies the feathering, flapping, and in-plane motions, while the equivalent centrifugal force load is applied. The centrifugal force is applied to the blades by means of an air cylinder. Since in the fixture the blades are stationary, the rotor shaft is pivoted to simulate actual operation. The main shaft is moving in an elliptical pattern to simulate the angular rotation of the blade in feathering and in flapping. During this activity, the shaft is also being twisted torsionally to simulate the lead-lag motion. In just a few months of continuous operation of the test fixture, we can log several thousand hours of helicopter time.
The elusive goal of a virtually zero-maintenance rotor system that can last throughout the helicopter's lifetime has been the dream of helicopter designers. Now, with advanced composite materials and proper design, this goal has become a reality in Windstar. A further advancement in Windstar's evolution was the development of the hingeless, bearingless composite tail rotor. Along with its gearbox, intermediate gearbox, and shafting, this composite tail rotor system proved to be a difficult, though extremely successful program. The next aspect we wish to focus on is the Windstar Fuselage. The cabin area is formed in the shape of an egg or teardrop, which is nature's most efficient low-speed aerodynamic shape. The eggshell of Windstar is a half-composite, half-steel structure providing great strength and light weight. This mix is the most cost-effective method of building a high-tech helicopter fuselage. Let's examine its construction.
There are two outer skin half molds employed in this process. In the first operation, the skin for each outer half is laid up. At the same time, a Nomex honeycomb core is pressure molded.
This gives you an idea of how the steel structure is integrated with the composite structure to create a much less expensive total unit. The idea of having a half-composite, half-steel fuselage is fail-safe and lightweight. 99% of the load is absorbed by the steel structure, while the whole fuselage, including the landing gear, weighs less than 200 pounds. That means that for 50 pounds per passenger, you not only have a structure to which you can mount all your hard points, engine, landing gear, transmission, but you also have a fuselage enclosure surrounding you. To substantiate the strength of Windstar's composite and steel fuselage structure, it was necessary to perform drop tests. There's a substantial stiffness contribution from the composite structure. However, we chose not to consider it in the drop tests. Our primary frame strength concern centers around the ability of the frame to absorb a severe impact without excessive damage to the roll cage structure surrounding the passengers. This primary structure must protect the passengers in a survivable impact.
In preparation for this drop test, G-meters were fastened to 3 points on the fuselage. The pilot's side of the cabin area, the mast area, and the engine mount area. Weights were bolted into the fuselage to simulate the rotor system, transmission, and power plant. Cranes were brought in to hold the fuselage structure in its proper position. During the drop test, the fuselage will swing into the ground in a 45-degree arc to provide a 40 feet per second impact at approximately 20 Gs. As you can see, no major damage was sustained. There is some crush in the lower frame area, but we must remember there is no landing gear protecting the frame. This is a worst-case test. We see that the G-meters on the pilot's side have all tripped due to the initial impact being felt at this point. A softer load was felt on the mast area due to the time-distance ratio from the point of impact. Only the 10G meter was tripped at this point. The transmission mounts, which are exactly the same as those on the actual ship, have not deflected significantly, nor have the longerons. None of the G-meters were tripped at the engine mount area. The fuselage is displaced laterally to the pilot side approximately 2 inches, but still there is no major violation of the passenger area.
Throughout the Windstar development program, many complex systems have been simplified, which not only adds to the marketability of the helicopter, but also, in many instances, has added to its safety. The helicopter is one of the safest flying devices ever conceived due to its inherent parachute, the rotor system itself. Helicopters can descend without power in auto-rotation and be flared to a complete stop prior to touchdown. During this auto-rotation descent, however, the pilot must be alert to maintain proper forward speed and rotor RPM while choosing his point of touchdown. If there were some way to improve this inherent parachute by giving the pilot significantly more time to react to the rapidly occurring events, flying in helicopters would take on a decidedly new dimension. And it does in Windstar. Windstar has made a major aviation breakthrough with its innovative Power-Assisted Landing Device, or PAL. The PAL system is activated by a protected switch on the pistol grip of the cyclic control stick and functions in the following manner. The Windstar transmission has an additional power input pad to which the PAL system is connected. A clutching mechanism engages the PAL system at this point. The PAL system, which is a geared turbine drive device, mates with the RPM and provides power at this transmission connection point. When the protected switch on the cyclic is flipped on, the PAL drive mechanism engages and almost instantaneously provides additional power. It's interesting to note that the height velocity diagrams for commercial helicopters are established during flight tests conducted by proficient test pilots. The average pilot may never gain the level of proficiency achieved by a test pilot. Therefore, the height velocity diagrams are somewhat unrealistic. However, the ability to dramatically enhance the auto-rotational performance of the helicopter by providing additional power during the auto-rotational regime of flight extends to the novice test pilot proficiency at the flick of a switch. After years of planning, engineering, systems testing, and modifications, we finally come to that moment of moments. The prototype is assembled and Windstar is ready to fly. For BJ and every other test pilot, this is what life is all about. But when you add the experience of the first run-up, the first trip through translation, the first climb-out, and the first auto-rotation with the dimension of creating this miracle machine, then you may be able to grasp the ultimate excitement this moment carried for Mr. Schramm and the entire Windstar development team.
The significance of the first liftoff to hover is important. In order for it to be accomplished, we must determine that the rotor system is in balance, the blades are tracking and properly balanced, the power plant is running correctly, the tail rotor has sufficient thrust, and there is no ground resonance problem. Ground resonance can occur in a multi-bladed articulated rotor and can destroy the ship almost immediately. In order to ensure against this, the stiffness and damping of the rotor systems must be correct, as well as the matching stiffness of the landing gear. Intermediate tests must be made as RPM builds to liftoff to ensure that no harmful resonance will occur. After extensive liftoff and hover tests have been successfully accomplished, we proceed to the next phase, translational lift. We begin to experience translational lift at approximately 15 miles per hour. Moving off the ground cushion and going into forward flight causes airflow changes in the rotor system. As the helicopter moves through translation, it gains additional lift up to 45 miles per hour, where parasite drag begins to take over. As you gain additional lift from forward flight, translational lift necessitates collective control changes, power changes, and tail rotor thrust changes. Stability of the rotor system and the amount of vibration are pilot cues. All controls must be adjusted for this regime of flight, especially if translational speed continues to be maintained just at the transition brake. At this point, the rotor may go out of track. If this occurs to any great extent, vibration could become severe. Going through translational lift for the first time is a very exciting experience for both the pilot and the designer, especially in a totally new machine.
When the preliminary airworthiness has been validated, we're ready to experience that thrill of thrills as we give birth to an era, as Windstar gives rise to her maiden voyage. The flight footage we have just seen was taken in April of 1986, just prior to the production of this video. Vertical Lift Technologies is continuing to document the intensive bench and flight testing procedures, and this ongoing record of advanced testing will be incorporated into additional video packages. Subsequent video releases will also include additional coverage of the power-assisted landing system and the extensive flight testing required for FAA certification. Windstar has met all objectives and has optimized size, advanced technology, and vision to create the next generation in helicopters. Windstar offers turbine engine performance with speeds of up to 150 miles per hour along with high altitude capability. Windstar provides added comfort for passengers with a quiet cabin and unmatched smoothness. And Windstar is affordable. And so now, on behalf of Vertical Lift Technologies and the entire Windstar team, this is Ron Anderson saying so long, and thanks for joining us.
If you and your company wish to make history, step into the future. Enter the exciting world of Windstar, the brand new, affordable helicopter that means business. Windstar is a revolution in progress. With demand for the product increasing, delivery will be on a first-come, first-served basis. To ensure your position to take delivery of your Windstar, you must act now by filling out the user questionnaire and returning it to us. Your questionnaire is enclosed in the information brochure, which you may request by phone. The technical information brochure for Windstar covers airframe and power plant features in great detail. Crashworthiness, airframe construction, powertrain, the all-composite hingeless bearingless rotor, and the power-assisted landing system are explained in layman's terms. Along with the philosophy behind the design of the power plant, 18 engine features are discussed. A unique see-through overlay presentation is employed to enable you to see aircraft systems and subsystems in their position in the airframe. Performance graphs and operational costs are covered, along with money-making possibilities. If you haven't already received your package, call now. There's a place reserved in the Windstar Revolution for you. Call Vertical Lift Technologies today. Call us now. Area code 602-345-7855. Or write to Vertical Lift Technologies, Kachina Business Center 1, 1830 West Drake Drive, Tempe, Arizona, 85283. And thank you.